All right, we're going to be talking about inverse functions today, and specifically focusing on how to find an equation for the function, for an inverse function. Okay, so yesterday we looked at three different ways in which you can determine if two functions are inverses. The first way was by looking at the tables of their ordered pairs. If their ordered pairs are just switches of each other, then those two inverses are functions. Graphically, if the two graphs are reflections of one another over the y equals x line, they are inverses. And then algebraically, if we look at the composite of their two functions, if they both simplify to x, then they are inverses. Okay, notation for the inverse is used a little -1. So it looks like an exponent, but it's not. Okay, so this, when you see it used with function notation, then that means inverse. So this says f inverse of x. Okay, so this is not being used as an exponent. Okay, so it does not mean like x to the -1 as an exponent does, where it means to do the reciprocal. Okay, all right, so that's the notation we're going to be using, f inverse of x. All right, so we're going to be looking at how to find an inverse equation. So 4 steps. Number 1, rewrite the function as a y equals. Number 2, swap the x and y variables. 3, solve for y. And then 4, rewrite your function using your inverse notation. Okay, so for 41, step 1 is you're going to write it as a y equals statement. So we're not going to use the function notation right now. So just rewrite it with y equals instead of f of x equals. Okay, step number 2, we're going to swap the x and the y variables. So instead of y equals x plus 4, it's going to be x equals y plus 4. Number 3, you are going to solve for y. So to solve for y, I would subtract 4 from both sides. And then this would be x minus 4 equals y. And then last step, rewrite it using your inverse notation. So this would be f inverse of x equals x minus 4. Okay, so this equation is the inverse equation to our original f of x. Okay, now something else just real quick, just so you can have a visual. So if this is our coordinate plane and we sketch my original f of x, so this is f of x, and then if you sketch the inverse, okay, then these two equations are inverses of each other because they are reflections. If you reflect the original f of x over the y equals x line, it will land on the inverse. Okay, so that's just kind of gives you a visual of what these two equations are doing. Okay, so 42, let's do the same thing. We're going to find the inverse. So first, rewrite it as a y equals statement. Okay, number 2, swap the x and the y. Now, just the x and the y. Don't move that whole term of 2x. You are just moving the 2x. So this becomes x equals 2y minus 1. Okay, step 3, we're going to solve for y. All right, so solve for y. First thing I'm going to do is I'm going to add 1 to both sides. So x plus 1 equals 2y. All right, then I'm going to divide by 2. So y equals x plus 1 divided by 2. And then last step, rewrite it, use your inverse notation. So instead of a y equals, I'm going to go f inverse of x equals x plus 1 over 2. Okay, now you may have written that a little bit differently depending on how you simplified that last step. Okay, so this could also be written as f inverse of x is 1/2 x plus 1/2. Okay, so take a second, look at both of those equations, and those are the same thing. So I just split that fraction and wrote it in two pieces. Okay, but those are still the same equation. Okay, 43. Now, 43, there's something new here that you haven't seen yet. You have f of x equals x to the sixth, and then there's this x is less than or equal to 0. What we are doing is we are restricting the domain. Okay, and there is a reason for that. That's not part of your equation. F of x equals x to the sixth. That's your equation. So if we go to start working on the inverse, it would be y equals x to the sixth. Okay, by restricting the domain, this is what happens. So when you have an equation, so let's say, for example, you have a parabola. Okay, a parabola is a function. All right, if I reflect that parabola over the y equals x line, I get a picture similar to this. Okay, now here's where the problem comes in. We are using function notation. We are calling these graphs functions. Okay, so the parabola, the original parabola, is a function. Okay, so by definition, for every x, there's exactly one y. Okay, or another way to think about it is if you do the vertical line test. So if you would draw vertical lines through this parabola, you can tell that each line is only going to intersect that parabola at one point. Okay, so that function passes the vertical line test, and so that is a function. However, when you look at the result, when you flip it, the sideways parabola, well, if I start doing vertical line tests, well, you've got all kinds of lines that intersect that equation in more than one place. Okay, so that makes this inverse graph fail as a function. Okay, so this one is not a function. Okay, so we can't have that. What you can do, though, is restrict the domain. So instead of seeing all of that parabola, we're only going to see a portion of it. Okay, so I'll show you what happens as far as the graph is concerned. Okay, so let's say, oops. Okay, so let's go back. Here's our coordinate plane. Okay, what if what if I say, well, you can only have points of your parabola that are 0 or greater. So then basically you have half of a parabola. Okay, well, this is my original function. That's still a function. If I do a vertical line test, I only intersect one place. So that is still considered a function. Now when I reflect it over the y equals x line, I now have something like this that shows up as its inverse. Well, now if we would do the vertical line test, you would only intersect that new graph at one point. Okay, each vertical line would only intersect it at one point. So now this inverse really is an inverse because it satisfies the definition of a function. Okay, so that's a lot to say that sometimes you're going to have a statement like this where your domain is restricted, and that's the reason why, is you're only going to look at a portion of the graph instead of the whole graph. Okay, so let's go back and let's talk about what the equation would be then for the inverse. Okay, so we already did the first step, y equals x to the sixth. Step number 2 is we're going to swap the x and the y. So this becomes x equals y to the sixth power. Step number 3, we're going to solve for y. Okay, so get y alone, we got to get rid of that exponent. Well, to get rid of that exponent, we're going to do the sixth root. Okay, so that sixth root cancels out the exponent, and this becomes the sixth root of x equals y. Okay, we are now solved for y, so now use your inverse function notation. So f inverse of x would equal the sixth root of x. Okay, so there is the equation for your inverse. All right, let's do one more here quickly, and then we will continue this conversation tomorrow, and we'll do a couple more for another example. Okay, so we're going to write this as y equals 2x to the fifth plus 3. We're going to swap the x and the y. So x equals 2y to the fifth plus 3. Okay, we're going to solve for y. So that's going to mean I want to move my 3 first. So I've got x minus 3 equals 2y to the fifth. Now I'm going to divide by 2. So x minus 3 divided by 2 is y to the fifth. And then finally, last step here, I'm going to get rid of that exponent. So I got to go fifth root both sides. Okay, so now that fifth root cancels out that exponent. So last step, write it as an inverse. F inverse of x equals the fifth root x minus 3 divided by 2. And here is your inverse. Okay, tomorrow we will talk about